Hello everyone, and welcome to the second episode of BMED 202. In this episode, we will look at some methods that can be used to determine different forces, namely the resultant forces and equilibrium forces. So let's dig in. Okay, so I am going to draw a diagram. This is an object. I'm going to draw a force being applied to the object. And in engineering drawing, or in building mechanical and engineering drawing, we use vectors to graphically determine forces and our resultant forces. I am going to draw a force graphically, and when doing so, we use a scale. So for example, let's say I'm representing a force of 3 newtons. I'll use a scale for example, 1 newtons would be equal to 1 centimeter. Let's use that scale. So this line would measure 3 centimeters since I'm representing 3 newtons. So this force is going in this direction, which is acting on this body, 3 newtons. Let's say that there's another force acting on the body at a 90-degree angle to the first force. Let's say that this force is 4 newtons and it's acting, I'm going to change the direction from north. I'm going to change this direction. I'm going to allow this force to act 60 degrees to the initial force. So this force, I'm going to even change the magnitude to about 5 newtons. As a result of that, this line will be measured as being 5 millimeters, or 5 centimeters rather, right? So here we have 2 forces acting on a body. Now, when we are trying to establish the resultant force of these 2 forces acting on this body, we will use what we call the parallelogram of forces, right? That method. So what we'll do is draw a parallel line to both lines at both ends of the vector. So right here at the end of this first vector, I'll draw a line parallel to this vector, and at the top I'll draw another line. So these lines meet here, and at this point I'm going to connect or draw a line connecting this point to the first line. Now this new force is referred to as the resultant force. And how can I find out this force? I'll simply measure the length of this diagonal in this parallelogram, and this is giving me 7 point, I'll assume this to be 7.25, right? So this new resultant force is 7.25 newtons. Let me write this correctly. And please note, I am drawing using the traditional method. I'm not using AutoCAD. As a result, this measurement may not be 100% accurate. This is an estimated result. The more accurate I draw, the more correct, or the more closer to being correct the answer will be. So this is the resultant force, or the resultant. Right? So as a result of these two forces acting on the body, you have now a new force that is called the resultant. So the body will now move in this direction. Right? So this body is not in a state of equilibrium due to the fact that it's in motion. Now, in order to bring this body in equilibrium, we have to now find an equal but opposite force to the resultant force, which would go in this direction. Now, there is a method that can be used to find or establish the equilibriant force, and this method is called the triangle of forces. Now, I am going to take these vectors and combine them, meaning use them to draw a triangle. So let's say this is the object once more, and it doesn't matter which vector you start with. So I'm going to start with the first one, and I'm going to go ahead with the other one. So this is my 3 newtons. And this is how we do the triangular method. We take the first vector, and at the end of the first vector, it will be the start of the second vector, which is 5 newtons, and we have to maintain the direction. So we have 5 newtons in the same direction as over there. So if you realize the direction is going this way, anti-clockwise, it doesn't matter which one you start with, it doesn't matter which direction you go in, it will correctly establish the resultant, the equilibriant force rather. So now the third force that would be needed to close off the triangle and thus bringing the object in a state of equilibrium will be this new force. So you have a force acting here, a force acting there. So this force is or should also be 7.25. Now, if this drawing does not give me 7.25, it simply means that my drawing is inaccurate, right? So it's not exactly giving me, but it should be 7.25 newtons. This 7.25 newtons is acting in the opposite direction as this resultant force. So I'll refer to this as the equilibriant. Right? So you have 3 newtons here. You have 5 newtons here. And you have my answer here, which is 7.25 newtons. So this is a triangle. This is a parallelogram of forces. This is the triangle of forces. Now, the triangle of forces is used to find the equilibriant. As I said, the resultant force is found by using the parallelogram of forces. Now, just a thing to note, if these forces were acting 90 degrees of each other, you would get a rectangle or a square depending on the magnitude of these forces. It is still referred to as the parallelogram of forces. Now, let's look at the polygon of forces. Now, the polygon of forces, this method is used when you have a number of forces acting on a body, whether pushing or pulling. So let's say I have a body here. Let me give it some more space. If I have a body here where a force is acting this direction, 2 newtons, and remember I'm drawing to scale, 2 newtons, then you have another force acting 4 newtons, and another force acting in this direction. Let me call this 5 newtons. All these 3 forces, if I combine all these forces like this, and they are connecting and forming a perfect triangle, it simply means that this body is in equilibrium. If they don't meet, if the 3 vectors don't start and end at the same point, then they are not in equilibrium, the object rather, and we'd have to find the equilibriant. Now, let's try to use the polygon of forces to see. All right. So this is the force, or this is the, let's start with force, this first 5 newtons. And remember, we start with the first force, and it doesn't matter which direction we go. And let me explain that again. So we have 5 newtons about here. It doesn't matter which one we use next. If we use 2, if we go in this direction, we are using the 4 first, then the 2 after. Let's do that. Remember, we're ending where we start. Last vector ends, new vector starts, and this is 4 newtons. And then you have a direction of 2 newtons. Going up. Obviously, this is 5, 4, 2. Obviously, this does not meet and form a triangle. As a result of this, this body is not in a state of equilibrium. In order for this body to be in a state of equilibrium, we have to find the equilibriant. The resultant of all these forces is not 0. So in order to find the equilibriant, we have to close the polygon. So we are continuing with the direction. So this line is now the equilibriant. Right? Once you apply this force over here, let me measure it. It is 7.2. Well, based on my drawing, that is. My drawing is not perfect, so it could be a bit over or a bit under that value. So this 7.2 newtons will bring the object. So let's draw this. Now, let's assume that this is parallel line is being transferred properly. Give me a minute. So let's transfer this parallel line. And measure 7.2. Well, I won't be able to measure 7.2 because I'm running out of space. So 7.2. So that is my equilibriant. If these were the measurements or the forces and the directions, this object would be in equilibrium, because it would mean that once you create the polygon with these four forces, they would connect. Right? So that's how the polygon of forces work, the triangle of forces, and the parallelogram of forces. You use the triangle of forces to, one, either find the equilibriant. So the equilibriant would be the third line in the triangle. Or you can alternatively try to find a triangle with three forces. If a triangle is not formed, then you have to proceed to form a polygon, which would give you the equilibriant. Please bear in mind that the equilibriant and the resultant force goes in the opposite direction. So in order to find the resultant force, you have to draw another vector in the opposite direction, but with the same magnitude. So I'm going to redraw this as a hidden detail line. That this was my equilibriant. This now would represent my resultant. So that's how these three methods are used to find the resultant and the equilibriant of various bodies that forces are acting on. So I hope you have grasped this concept. Have a wonderful day.